Okay, let's look at a rolling disc that's rolling on the ground, and we apply a moment of 35 foot-pounds to this disc. We're going to say the center of mass of this disc is at point G, and the radius of this cylinder or this disc is going to be 1.25 feet. Now we're going to also say it weighs 50 pounds and it has a radius of gyration of 0.7 feet. And we want to determine what its acceleration of the center of mass is. So it's A sub G. And we're given a few other things. We're told that the coefficient of static friction is 0.3. The coefficient of kinetic friction is 0.25. So how do we go about this? Well, there's a trick to this problem when we have to assume it rolls without slipping and then check our assumption. But first, like always, we draw our free body diagram. And our free body diagram is going to identify the forces and our accelerations. So for our force side of this free body diagrams, we're going to have a weight that goes through our center of mass. This weight, because we're in the English units, is just 50 pounds. We're going to have a frictional force that acts in this direction. Why this direction? Because while this is rotating, friction opposes the motion, and it's pushing off. So the motion is going like this. So at this point right here, our motion is towards the left. So friction opposes that and moves towards. That's why it's pointed towards the right in this direction. And then we're also going to have a normal force that comes up like this, and we're going to have our frictional force. And we have to identify the moment. So this 35 foot-pounds. And now, like always, our other type of diagram is our kinematic diagram. And we're going to identify our accelerations and our moments of inertia and all types of accelerations. So our acceleration of our center of mass is going to be in this direction. As we apply this moment, our our acceleration of our center of mass is going to be towards the right. So our mass is going to be 50 over g times our acceleration. And now, as we move this, we're also going to have a rotation about our center of mass of Ig alpha. And this Ig is our moment of inertia about point G times our angular acceleration. And it's going in the same direction as this cylinder rolls. So it's rolling counterclockwise and its mass is going to the right. So we know that we're rolling this way, so this is our positive angular acceleration, and our center of mass is moving towards the right, so this is our positive center of mass. Now we just want to look at all our different equations. We want to look at the sum of the forces in the x is equal to the mass times the acceleration in the x. Our sum of the forces in the y is equal to our mass times our acceleration in the y. And our sum of the moments about our center of mass, so g, is equal to our moment of inertia of g times alpha. Now let's look at some of the forces in the y. We're equal to frictional force. This is positive. So our frictional force is positive, and that's our only force in our x direction. So this is equal to 50 over g times the acceleration of our center of mass. Now our sum of the forces in the y direction, so we're going to have a positive normal force minus 50 because our 50 is our weight and it's pointed down, is equal to 0. And why is this equal to 0? Well, we have no acceleration in the y direction. So now we have the sum of the moments about our center of mass. Now if we look at our center of mass, it's this point right here. So the only moments that we have to deal with are this moment 35 foot-pound moment and this frictional force. The weight and the normal force that the ground exerts back on this rolling cylinder go directly through our center of mass. So if it rotates this way, we're going to have a positive 35, and we're going to have a minus frictional force times the perpendicular distance, and this perpendicular distance is 1.25 feet. And this is equal to this moment of inertia times alpha, and this is positive. So our moment of inertia, since we're given a radius of gyration, is going to be equal to m, which is 50 over g, times this radius of gyration squared. So whenever we're given a radius of gyration, it's going to be equal to our moment of inertia about point g is equal to our mass times our, not times the radius, mass times this radius of gyration squared. So our radius of gyration is 0.7 feet. So 0.7 squared alpha. Now, again, we have some sort of problem. We don't know what this frictional force is. We don't know what this acceleration is. We can figure out what this normal force is. We know that our normal force is just going to be 50. But we don't know what alpha is. So with these two equations, the sum of the forces in the x and the sum of the moments about point g, we have three unknowns and only two equations. So what we're going to do is we're going to assume that this does not slip as it moves. So we assume no slip. And when we assume no slip, we get this fourth equation that our acceleration of our center of mass is equal to our angular acceleration times our radius. And this is equal to our angular acceleration times 1.25 feet. So now we can substitute this back into the sum of the forces in the x direction, and we get this expression. And then we can substitute this expression for the frictional force right here into this right here. And when we do this, we're going to have, I guess I'll write it out, 35 minus 50 over g times 1.25 alpha times 1.25. So this entire equation is multiplied by 1.25, and it's equal to 50. Oops, I'm out of room. So this is equal to 50 over g times 0.7 alpha. So what I did was just substitute this frictional force in to this variable, this frictional force variable right here, and we have an entire equation in terms of alpha. And we can just solve for alpha, and we can get alpha is equal to 11 radians per second squared. And because we now know alpha, we can substitute alpha into this frictional force right here, and we can get a frictional force which is equal to 21.3 pounds. But now we have to check if this assumption that we made that it did not slip was valid. So in order to check our assumption, we use this equation. We say that this frictional force must be less than or equal to our coefficient of static friction times our the normal force. And we have both of these numbers. We have this coefficient of friction, which is 0.3, and this normal force, which is 50, and this frictional force, which is 21.3. So we have to check if this 21.3 is less than the coefficient of static friction times our normal force. And if we do this, this is not true. This is equal to 15, and 21.3 is not less than or equal to 15. So our assumption was false, or it was not true. This means that the wheel slips as it rolls. And now, because it slips as it rolls, we have another expression for our frictional force. We have that our frictional force is equal to the coefficient of kinetic friction times our normal force. So we have to disregard these previous results. So we don't want to use this result, and we don't want to use this result, because the assumption that we got those results under is not true. But we do know that since that assumption is not true, we can use this expression for our frictional force. And so now our frictional force is going to be equal to 0.25 times 50. And our frictional force is going to be equal to 12.5 pounds. But we still don't know what our angular acceleration is and what our acceleration of this center of mass is. But we now know our frictional force. So with this frictional force, we can go back to this sum of the forces in the x direction. We know our frictional force right here is this 12.5, which is equal to 50 over g times this acceleration of g. And we can get that our acceleration of g, just by using this frictional force, our acceleration of g is going to be equal to 8.05 feet per second squared. And for completeness, we can go back in and we can solve our expression right up here. We can solve this expression for alpha, and we can get an angular acceleration which is equal to 25.5 radians per second squared. So the important thing of this problem is, at first we always assume it doesn't slip. So we have our sums of forces in the x, our sums of forces in the y, and the sum of our moments. And the fourth equation we need to use is this assumption that it doesn't slip. Now, when we solve for whatever we're looking for, we then need to check if this assumption is valid. So in order to check if this assumption is valid, we use this equation. This frictional force is less than or equal to the coefficient of static friction times the normal force. And if this assumption is correct, we're done with the problem. Our answers are correct. If this assumption, this check is not true, and our frictional force is greater, like it was here, then we need to throw out the results we had and use this expression for the frictional force. And I know a lot of people like to right away say a frictional force is equal to this coefficient of static friction times the normal force right over here. But we don't want to do that in this problem because we don't know if it slips or if it doesn't slip. And if it slips or if it doesn't slip, we need to use different coefficients of friction. So that's why we want to check our assumption this way. And then if this assumption is not true, we want to redo our results using this expression right here, that the frictional force is equal to the coefficient of kinetic friction times the normal force. And we can resubstitute into all the equations that we have right up here to get our final answers.